discuss the third module, algebraic structures of discrete mathematical structures. Today we are going to concentrate on what is an algebraic binary operation and what are the definitions and some of the examples we are going to discuss regarding binary operations. A binary operation means a binary operation on a set is everywhere defined a function. That is, it is nothing but a function from A cross A to A. Generally, the operation is denoted by star on A, then A star A belongs to A for every A comma B belongs to A. So it is nothing but a binary operation is nothing but a function which is defined from A cross A. So whenever if you are taking A cross A, then the set is consisting, suppose if I am taking A cross A, so here all the elements which are ordered pairs, and it is related to one set. See, this is a function from A cross A to A cross A to A. So here A cross A is nothing but set of all ordered pairs. So those ordered pairs we are going to represent A star B, because we are denoting the binary operation with the symbol star. So A star B belongs to A, then for every A comma B belongs to A. So now let us go for this. So this is nothing but a function which is defined from A cross A to A. So now let us go for an example. So the set is a integer set, and we are going to define the relation between two elements of this set, x star y as x plus y. Now we have to verify whether star is a binary operation or not. Means that you have to consider any two elements from the set Z, and if you are going to apply x star y, that is nothing but x plus y, so which is a member in that or not, we have to verify. So here, if you are considering any two elements from the set of integers, then those two elements are, let us consider 3, 5. So 3 star 5 can be represented as 3 plus 5, which is equals to 8. So which is also a member in A. So we can say that the binary operation star is a binary operation. So here we are considering any two elements means nothing but the integers alone. Then addition of integers is also an integer. So star is a binary operation. Okay, now let us go for the other one. A is equals to a real number system, and then x star y, relation between two elements is x divides y. Then is star a binary operation? Is star a binary operation or not? So here we have to consider any two elements. So let us say I am taking 2, 4 belongs to A. So the binary operation is what we are going to say, that 2 star 4 is 2 divides 4. That is 4 by 2. So which is equals to 2. 2 is nothing but another real number which belongs to A. Instead of these two numbers, this is the property. Here it is mentioned. Now let us consider two elements. I am going to consider 0, 3. Let us say 0, 2. Let us say belongs to A. Now, so there is a star 2 is 2. 0 divides 2. Which is nothing but 2 by 0, which is infinity, which is a meaningless. That means we are saying that which is not a binary operation. Star is not defined. Star is not defined for these two elements. Or else if you are making 0 star 3, 0 star anything, 0 star anything, we are going to get that divides operation between those two numbers does not define. So we can say that star is not a binary operation. Star is not a binary operation. Now let us go for the other one. So here subtraction will be there. So here positive integer set. A is a positive integer set. Now any two elements if I am considering, so the difference, if the difference is a member, then we can say that it is a binary operation. Otherwise it is not a binary operation. So here I am taking the positive integers. Z plus means positive integers. So the elements in Z plus 1, 2, 3 and so on, it will be there. So now we have to consider any two elements from Z plus. Let us, I am taking 1, 2 belongs to Z plus A. A is nothing but positive integers. So if 1 star 2 can be represented as x star y is equals to x minus y. So it is 1 minus 2. So what I am going to get? Minus 1. Minus 1 does not belongs to Z plus. Does not belongs to Z plus. So here we are saying that the star, which is nothing but a difference of two numbers, which is not a binary operation. Like that you can consider any lesser number first and the next higher number, that's 5 and 10 if I am considering belongs to Z plus. So here the difference I am going to get a negative value, so which does not belongs to Z plus, which does not belongs to a positive integer. The difference of two positive integers need not be a positive integer. So the star is not a binary operation. Now let us go for the other one. So here let A set is equals to Z and now the thing is there is a star x star y is nothing but the maximum among these two. Now we have to verify whether it is a binary operation or not. So here I am just considering another one. The Z is a integer set I have to consider. Then any two elements if I am considering. Let us say 0, 6. 6 elements are from the set Z and I am just saying that 0 star 6, which is nothing but maximum element of 0, 6, which is 6. So which is nothing but belongs to Z. See, anyhow we have to consider two elements from the given set, and there is a relation is nothing but the maximum value among those two. Definitely it is an integer. So here star is a binary operation. Suppose if you are going to consider another example, if S is a finite set and A is a power set of S. So set A is consisting, suppose A is equals to, I am just taking 1, 2, 3. Then P of S is, sorry, not A, this is only S. So it is S. Then P of S is equals to null set. And the next is singleton 1, singleton 2, singleton 3, next 1, 2, 1, 2, next 1, 3, next 2, 3, next the given set itself 1, 2, 3, 1, 2, 3. This is the P of S. That is nothing but this is given as A. Now I am considering any two elements from this set. Here x star y is union of those two sets. Let us consider I am taking 2 is one set and another one is, let us take 1, 3. 2 elements from the set A. A is nothing but power set of S. So, which is nothing but A. Then 2 star and 1 3, which is nothing but 2 and union of 1 comma 3. Subsequently, we are going to get 1 2 3, which is nothing but a member in P of S, which is nothing but a member in P of S, which is equals to A, which is equals to A. Any two elements if you are going to consider from A, two elements means here it is nothing but a sets, two subsets we have to consider from A. Then the union of those two subsets is also a member in that. So we can say that star is a binary operation. Any two numbers if you are going to consider, let us take 1, 2, 3 and I am taking 2. So then belongs to A. Then if we are going to say that there is a binary operation, let us say star 2 is nothing but union of these two, which is nothing but 1, 2, 3 itself is a member in A. So we can say that this star is a binary operation. So here any elements between two elements, star operation is nothing but union. So we have to consider from the power set. Then automatically it is also a binary operation. Now there are some more problems will be there. The thing is the binary operation is given and which is going to defined on a set of integers whether it is satisfying commutative or associative properties. Commutative and associative properties. So commutative property means, see, if I am taking x comma y belongs to z, then x star y is equals to y star x. Then we can say that this is a condition is satisfies. Then we can say that the star, the binary operation is a commutative. And associative means if I am going to consider any three elements from the integer set, then this is x star y star z is equals to x star y star z. If this condition is satisfies, then we can say that the binary operation is associative. So for that now we have to verify whether this is satisfies a commutative property or associative property. Okay, now we have to verify. So here let us go for, and I am just considering any two element. Let us say I am just taking 2 comma minus 2 belongs to integer set. Then what I am taking 2 star minus 2, which is equals to here. This is nothing but the difference of 2. So it is 2 minus of minus 2. Y is equals to minus 2, which is equals to 4. And if I am taking in another way, minus 2 star 2, which is equals to minus 2, which is minus 4. So here, this condition, that is a star, x star y is not equals to y star x. So here, a star b is equal to 4, whereas b star a is equals to minus 4. So x star y is not equals to y star x. So this is, we are saying that the binary operation is not a commutative, So we can say that it is not commutative on Z, the set of integers. Similarly, the associative property, if I am going to consider, the associative property, any three elements, you have to consider from the integer set. Okay, let us take, I am just taking 1, minus 2 and 3. If I am considering three elements in the set of integers, then what I am taking 1 star, minus 2 star and 3, which is equals to 1 star, minus 2 star 3. I am just verifying this. What is this value is 1 star, and this is -2, -3, and this is 1 minus of -2, first 2, and star 3. And here it is 1 star -5, and here it is 1 plus 2, it is 3 star -3. So what about this? This is 1 minus of -5, so it is 3 minus of -3. So what I am going to get? This is a +6, and this is also +6. +6 and +6. So if I am considering for the some specific values of if I am taking x is this, y is this, and z is this, it is satisfying associative property. But if I am going for another set of values, so let us take all are negatives. All are negatives. So if I am taking -1, -2, -3. So for that, if I am going to calculate this, so here instead of taking all the things, I am just considering -1, -2, -3. So if I am taking like this, -1, -2, then -1, and then I am going to write like this. So here -1, so -2, minus of minus, it is plus, and then this will become, so it is -1 plus 2, -1 plus 2, and star -3, Now this is going to be verified. Let us say this is -1 star plus 1, and then this is 1 star -3. So here what I am going to get? This is -1 -1, 1 minus of -3, it is +3. -2 is equals to 4, which is not correct. So even though some set of values the associativeness is proven is same, but not for all. So this binary operation is not commutative as well as not associative. So now what are the properties of a binary operators? So here the binary operator, let us say star is a binary operator. If it satisfies this condition, then we can say that it is a commutative. It satisfies or star is said to be commutative, or binary operation is said to be commutative. And whereas this condition is satisfied, then we can say that the binary operation is associative. And whereas it satisfies this, then we can say that the binary operation is idempotent. So these are some of the properties that we discussed. And now the binary operation is commutative or associative. On that we are going to discuss some more problems. Okay. Now on Z, so x star y is equals to, this is given. X star y is equals to x plus y plus 2. And another one is x star y is equals to xy. And x star y is xy by 3. And we have to verify under this whether it is a commutative and associative or not. So first one is, see here z plus. So we are going to consider the set is like this. So now the thing is all are positives. So here the set is defined as positive integers. So the operation is also positive. So naturally we can say that it is commutative as well as associative. So any two elements if I am considering. So because the addition property, because the operation addition will be there between the numbers and +2 will be there. So plus or addition is satisfying the commutativeness as well as the associativeness. So obviously we can get under this binary operation is associative as well as commutative. Now observe the second one. It is defined on this set of positive integers. If I am taking then automatically this is also by seeing itself, we can say that satisfies associative as well as the commutative property. But we have to verify under the integer set, because the integer set is consisting positive values as well as the negative values. So if I am taking the negative values, how it will be, then we have to verify. So here commutativeness is automatically understood. So if I am taking any two numbers, okay, x, y, let us say -2 and 6, if I am taking, then belongs to z. Then if I am taking -2 star 6 is equals to -2 into 6, which is equals to -12. And whereas 6 star -2 is, so it is a 6 into -2, which is equals to -12. That means it is nothing but a product of two numbers, either A into B or B into A. Then we are going to get the same number. So automatically it satisfies the commutative law. But whereas the associative law, if you are going to consider whether it satisfies or not, we have to verify. Anyhow, here it will be xy will be there. Now we have to verify any three elements. I am just considering -1, -2, -3 belongs to z. So now we have to verify whether the condition is -1 star -2 star 3, and which is equal to or not equal to. So here -1 star -2 star -3, and which is -1 star -2 star -3. Whether these two are equal or not, we have to verify. So this is the product, it is given. The product is given. So we have to, what is this function value is? It's not that. Okay. This is xy. So here I am just taking, what is this? -1, -2, -3 belongs to, what is this? Here it is z. Okay. Belongs to z. Then -1 star -2 star -3, which is equals to -1 star -2 star -3. Just verify. So -1 into, then it is 6. Then it is, this is 2 into -3. So what I am going to get, this is -6, and this is also -6. Suppose if I am going to consider any one is the positive, let us say this is a satisfying associativeness. Suppose if I am going to consider any one, let us say I am just taking +3, just to verify. So it is -6, and the next one is it is 2, and then it is +6. So what I am going to get, one is +6 and 2, and this is also +6. So it is satisfying. So we can say that the binary operation star is associative. And next another one is another one is on the real number system, x star y is equals to xy by 3. So here it will be just we have to consider the any two elements, and obviously it is a commutative law. Just it is nothing but just we are going to consider, see here xy by 3 real numbers if I am taking. So for any two real numbers, so by 3 the product of real numbers is again a real number, and if I am going to divide with another real number, the divisibility of two real numbers is again a real number. So the thing is, whether it is in any way in real number system, if you consider in any way, either x into y or y into x, so it is going to be satisfied the commutative law. So that is given here. So that is star y. So the binary operation is satisfying commutative law. And next, the associativeness. So here any three elements, if I am considering, let us say -3, and next -6, and 2, let us say, belongs to R, then here minus 3 star and minus 6 and the next one is star 2 is equals to minus 3 star minus 6 star 2. Let us, this is, what is this, x into y by 3. So it is nothing but 6 star 2 and this is minus 3. Then this will become minus 2 to minus 4 I am going to get. So it is 6 into 2 by 3. Then it is minus 3 minus 4 by 3. So what I am going to get 4 and here also 4. So in any way we are going to get a condition is going to be satisfied. So we can say that this is going to be associative property. Satisfies the associative property. So like that. So the remaining 2 also we can do either whether it is satisfies or not, the associative as well as the commutative properties. Now, still so far we discussed the binary operation which is a commutative or which is a associative by using some of the examples. Now, the other thing is, what is a groupoid? What is a semigroup? What is a monoid? What is a monoid? So those things we are going to know now. Let us S star be an algebraic structure in which S is a non-empty set and star is a binary operation and S is closed under the binary operation. In such a case, such a structure, S is a closed under the binary operation, such a structure which is consisting a non-empty set, and a binary operation defined in S is called a groupoid. See here, let S comma star be an algebraic structure in which S is a non-empty set and a star is a binary operation and S is closed under the binary operation. So whatever the 2 elements if you are going to consider from S under binary operation star, S is going to be closed. Such structure, such an algebraic structure consisting a non-empty set S and a binary operation defined in S is called a groupoid. So now let us go for an algebraic structure. S comma star is called semigroup when it is saying that is a monoid and when it is saying a semigroup. So now an algebraic structure S comma star is said to be semigroup under the binary operation star. So first of all, it should satisfy these 2 conditions. One is it is closed under the binary operation star and it is associative. So whenever the binary operation satisfying or the star is going to satisfy these 2 conditions, closure as well as closure or binary operation and next the associative property, then we can say that the algebraic system or S is said to be a semigroup. The algebraic structure S comma star is said to be semigroup if it satisfies the following condition. One is a closed or binary operation. Okay, star is closed. And next the associativeness, then it is said to be some semigroup. And when we say that the algebraic structure is called a monoid, so a semigroup is said to be monoid. If it is having an identity element. See, these 2 are obvious. These 2 is true for semigroup. So a semigroup is said to be monoid if it is having an identity element. Then that semigroup is called a monoid. See here the binary operation we are going to consider here. Then after that the semigroup we are going to consider. Then after that monoid. After that monoid. So here, or else another way we can say that a algebraic structure S comma star is called a monoid if the binary operation is closed and the binary operation is associate and there exists an identity element E in the set S with the property that E star A is equals to A star E is equal to A. Then this is true for all A belongs to S. This is true for all A belongs to S. Then we can say such an algebraic structure is called a monoid. So this is the things that we are going to consider. Now let us go for the problems on semigroup and monoid. Now see here the binary operation is mentioned here as well as here. This is, let us say, figure 1 and this is figure 2. Now from the first figure we have to verify whether the set, instead of G, what I am saying, how A comma star. This is the algebraic structure. We have to verify whether it is a semigroup for this as well as for this. And the binary operation is defined in the table. Means that X star X is equals to X. X star Y is equal to Y. Y star X is equal to X. Y star Y is equal to X. This is given in the table itself. And we have to verify whether the binary operation star is satisfying associativeness or not. Associative or not. So for that, let us consider 3 elements we have to consider. Where are the 3 elements? 3 elements are not there. Okay, let us, one element is going to be repeated. Let us, I am just taking X comma Y and take other element. Let us say X only belongs to A. Now we have to consider X star Y and star X. This is for associativeness. We have to verify. Then this is X star Y star X. Y star X. What is X star Y? X star Y is Y. So this is Y star X. And this is X star. What about Y star X? Y star X is X. Y star X is X. What about Y star X? Y star X is X. What about X star X is also X. Also X. If I am taking 3 elements like that. Suppose if I am considering 3 elements are like this. Then what about this? X star Y is equals to X star Y star Y. We have to verify. What about X star Y? It is X and then X star Y. X star Y. This is Y star Y. So what is X star X is? X star X is X and Y star Y is also X. Is also X. So in any order if I am going to consider 3 elements, so it satisfies the associative property. So we can say that it is a semigroup and moreover and the binary operation is closed. See, any 2 elements if I am going to consider X comma Y belongs to A. What about X star Y is Y. So here whatever the binary operation, any 2 elements if I am considering, all the elements here which are members in the set A. Which are members in the set A. So automatically the binary operation is closed. Binary operation is closed. So we can say that the given set together with the binary operation star is a semigroup. Is a semigroup. Now we have to verify whether it is a monoid or not. Whether it is a monoid or not. So it is a semigroup already two conditions are satisfied. Now we have to verify whether it is having the identity element or not. Whether it is having an identity element or not. Identity element means if you are going to multiply any number with that element, that number will be same we are going to get. See here, if I am taking that x star, I am just taking x star x is equal to x, and next x star y. See, x star y, I am going to get y, okay, for the first row, and the second one if I am taking y star x. Suppose if I am considering the first one, I am just taking x as the identity element, because x star x is equal to x I am getting, x star y is equal to y I am getting. Then y star x, suppose if it is the identity element, I have to get y. So y star x is equal to x will be there. X will be there. So x is not an identity element here. If x is an identity element, then y star x is equals to, I am going to get it is y. If it is having y, I can say that x is the identity element. So for this first table, there is no identity element. That means a semi-group which does not have an identity element, so we can say that it is not a monoid. So that is the first table. And suppose if I am going to consider the second table, let us go for the table 2. In this table, I am just verifying once again the associativeness. So associativeness in any order if I am taking, let us go for the same way. So I am just taking x and y and x. So here it am x belongs to A, then x star y star x is equals to x star y star x. So what is the x star? This is x star. What about y star x is? Y star x is y, and x star y is y and star x. X star y is y, y star x is y. Y star x is a y. So it is satisfying the associative property. In any order we can say that it is satisfying associative. And of course all the elements which are the binary operation. So here star operation if I am considering, then the resulting values are only the members of the given set. So automatically it is closed. By seeing the table itself, we can say that it is closed. And now it satisfies associative. So we can say that for the second table, A comma star is a semigroup. Now we have to verify for the second table whether A is a monoid or not. Now observe this, x star x is a, see here what I am going to get, x star x is equal to x star y is equals to y, and the next another one is x star y. See here I am taking y star x is equals to y. Now y star y is equals to x. So from this what I am going to get, this is wherever, just ignore this, wherever x will be there. So the same elements I am going to get, x and star y, I am getting y, and y star x. So here x acts as an identity element. So x belongs to A, and which is acts as an identity element. So for this case, we can say that the given set together with the binary operation star is a monoid. So these are the things that we are going to know this. First one is what is an binary operation and what are the properties of the binary operation, and now what is a semi-group and what is a monoid. Now we are going to extend further. Next another concept will be there, the groups. So now what is a group? So here G is a non-empty set and a star is any binary operation. Then G is called a group. G is called a group under the binary operation star if these conditions are going to be satisfied. These two conditions are going to be satisfied. So one is it is closed under binary operation, it is closed under the operation star. It is associative under the same operation, and there is an element, identity element will be there in the group, in the G non-empty set, and every element if I am considering, definitely it has one inverse is exist. Every element will have inverse. So then we can say that the non-empty set together with the binary operation is called a group. Or else we can say that a monoid is said to be, these are three properties is nothing but a monoid properties. So instead of these three properties, we are going to say a monoid is said to be a group, or a semigroup is said to be a group. If semigroup is said to be a group means if it has an identity element and every element will have its inverse. Suppose if I am saying that a monoid is said to be a group. A monoid is said to be a group. Every element A belongs to G. Every element A belongs to Z. Definitely there is an element A dash with the property A star A dash or A dash star A is equals to identity element. So here whenever this is going to be exist, then we can say that A inverse is called, A dash is called inverse of A under the binary operation star. So this is the group definition. And to simplify the notation, A star B, when there is no ambiguity, we write A square as A star A, and A is a group under binary operation star, will denoted by G comma star, or simply we are going to write G. And next, G is said to be commutative. A group is said to be a abelian group if it satisfies under the same binary operation, it is going to be satisfies the commutative law. That is A star B is equals to B star A. This is true for every A comma B belongs to G. This is true for every A comma B belongs to G. So whenever it is true, then we can say that that group is said to be abelian group. So here, for the sake of simplicity, we can write it instead of A star B. Sometimes we are going to write it as AB, and it's not and whatever the operation that is going to be performed, if it is multiplication will be there, the binary operation is multiplication, then we are going to mention like this. AB is equal AB, A star is a multiplication, then A star B is equal to AB, and this is BA. So under that, a group is said to be abelian group. Then we are going to satisfy this property. And now a group is said to be a finite group. A group is said to be finite if G is a finite set. If it is infinite, then we can say that it is not a finite group, and then the cardinality of Z must be a finite. Let the finite value is n. So a group is said to be a finite group if G is a finite. Let us say if I am taking, it is having n number of elements, then we can write the order of the cardinality of the graph. This we are going to pronounce as the cardinality of the group G, cardinality of the group G. So R is the number of elements in the G, which is mentioned as n, or we can write as order of G. Is equals to n. So a group G comma star where G is not a finite set, then it is known as a infinite group. If G is a finite, no problem, it is a finite group. If it is infinite, G is infinite, then we can say that it is an infinite group. It is an infinite group. So here, what are the things that we concentrated? The binary operation, and then the associative properties. Then after that, it is having the identity element. This is monoid, and after that, it is a group, and after that, it is a abelian group. It is a abelian group. The associatives are the binary operation which satisfies the associativeness, then it is known as a semigroup. A semigroup which is having an identity element is known as a monoid. A monoid which is having every element, which is having a monoid, every element is having its own inverse, then it is a group. A group in which satisfies the binary operation, satisfies the commutative law, then we can say that it is an abelian group. Abelian group. So this is the way that we are going to extend the binary operation, satisfies some conditions, some properties, we can say one name we are going to assign, and we are going to extending the properties which the binary operation is going to be satisfied. So in the next class, we are going to discuss some problems on groups as well as abelian groups. And next, some of the properties of the groups that we are going to discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.